Hi everyone, and this is Sandeep. You are watching Samyan's Academy, and in this session we are going to discuss about metals and non-metals part 2. So let us start. Properties of ionic compounds. So to know the properties of ionic compounds, here we are performing two activities. So in the first activity, what we are doing, you are taking the ionic compounds like sodium chloride, potassium chloride, magnesium chloride in spatula. Just you heat it and observe, and it is melting or not. Okay, after some time you observe that the color of the flame is changes, but the ionic compound do not melt. From this activity we know that ionic compounds are having high melting point, right? And to know the ionic salt solutions carries electric current, so we are doing this activity. So to this you take one spoon of salt and add it into the 100 ml of water and make it salt solution. To this you add two electrodes, and one electrode is connected with the negative terminal of the battery, other electrode is connected with the positive terminal of the battery, and switch key and bulb. When you connect like this, just you switch on it and the bulb get glows. So this indicates that ionic salt solution, when it is dissolved in the water, it dissociated into ions. So for example, NaCl, when you dissolve NaCl into water, what will happen? The NaCl dissociated into Na plus and Cl minus. Okay, this Na, yeah, these two get dissociated into Na plus and Cl minus. Okay, because of these ions, the current is passed through these ions and form this electric circuit is closed. Okay, then the bulb gets glows. From these two activities we confirm that. So what we have done here, so takes all samples like sodium chloride, potassium iodide, barium chloride, etc. Heat each sample on the flame using a spatula. They do not melt. Flame color changes, but sodium chloride gives orange yellow color, potassium iodide gives violet color, and barium chloride gives a green color. And one more activity we perform, that make a circuit and insert the electrodes into a solution of each salt, then salt solutions conduct electricity. Properties of ionic compounds, in that we are discussing here physical nature. They are solids and hard due to strong force of attraction between positive and negative ions. And one more property is they are brittle and break into pieces. Okay, the physical nature of ionic compounds are white color, solid, crystalline. And why these solid crystals are formed? Because of the charged ions, right? The positive metal ion and the negative non-metal ion combined by strong electrostatic force of attraction. Due to that strong electrostatic attraction force, and they are form like crystalline solid, they are hard in nature. So when you hammer it, it will get brittle, right? They are brittle and break into pieces. And high melting and boiling points, this is because much energy is required to break the strong interionic attractions. Okay, and now they have given here sodium chloride melting point here is how much here, 1074 kelvins, and boiling point is 1686 kelvin. Why these compounds are showing high boiling points and high melting point? Because of strong interionic attraction forces. Because of that strong attraction forces, to break that bond between the sodium plus and the chlorine minus, we require the more energy, so that here melting point and boiling points are high, right? Next is solubility. All ionic compounds are ionic salts dissolved in the water, right? All are soluble in the water except some and also they insoluble in kerosene and petrol. Okay, ionic compounds are soluble in water, but they are insoluble in kerosene and oil. Next, here we have the conduction of electricity. It occurs through a solution by the movement of charged particles. A solution of an ionic compound in water contains ions. When electricity is passed, ions moves to opposite electrodes. Okay, now so here we have taken one jar, and in this we have salt water. So we kept two electrodes, and which are connected to the bulb and the battery. Okay, when you add the more salt, the bulb glows more. So this indicates that this salt water, when it is dissolved in the water, it split into ions. Like salt water means you take NaCl. NaCl, sodium chloride salt, when you dissolve in the water, it split into sodium plus ion and chloride minus ion. Okay, and due to this formation of charges, the electricity is passed through that ions and circuit is closed and the bulb glows. So this indicates that ionic compounds in solution state, it allows the electricity through it, means it conducts the electricity in solution form. Right, move on to the next one. Solid ionic compound do not conduct electricity. Okay, and note, you have to note here, the solid state or solid salt do not conduct electricity. Then solid, this ionic compound, when it is in molten form or when it is in the dissolved form in the water, then only it will conduct the electricity. Okay, in liquid state only it will split into ions, then only the ions are responsible for the electric current, right? In solid ionic compound, ions remains as neutral, NaCl, right? So because of that, they do not conduct the electricity. Now here given the, because ions cannot move due to the rigidity, but they conduct electricity in molten state because electrostatic force of attraction between the ions overcome due to heat. Thus the ions move freely and conduct the electricity. Okay, so move on to the next one. Here I have summarized these properties of ionic compounds. They are formed by the transfer of electrons and are made up of ions. How the ionic compounds are forming? Because of transfer of electrons from metal to non-metal. They are crystalline solids. They look like as white crystalline solids, right? They have high melting point and boiling point. They are soluble in the water but insoluble in organic solvents like petrol, kerosene, etc. They conduct electricity in molten state or in solution state, and these are the properties of ionic compounds. Now, extraction of metals from its minerals. Okay, so occurrence of metals. So before that, we have to know that what is mineral and what is ore. I have given here, these are some ores. The earth crust is a major source of the metals. So where do we get from all these metals? From the earth crust. And these are also some of the metals we can extract from the seawater also, like sodium chloride, potassium chloride, halides, right, which are present in the form of halides, which can be extract from the seawater also, sodium chloride, magnesium chloride, etc. The elements are now what is mineral? Let us see now. The elements are compounds which occur naturally in the earth's crust are called minerals, and these are the minerals. Okay, and the elements are compounds. These are occur naturally where we can where these minerals are available in the earth crust. Okay, and the elements are compounds which occur naturally in the earth crust are called as minerals. Here we have some minerals. And what is ore? Ore means the minerals that contain a very high percentage of particular matter are called ores. Okay, for example, you take copper sulfide ore, Cu2s. This is also called as galena. Okay, mercury sulfide, that is cinnabar. In cinnabar ore, which one is high in percentage? The mercury metal is higher in the percentage. That is we called as a ore. Okay, ore means the percentage of particular metal is, the concentration of the particular metal is high, right? The minerals that contain a very high percentage of a particular metal are called ores. Okay, here I have given some ores here. Now, enrichment of ores. Okay, before extraction of metals from this ore, first you have to do the first step, enrichment of ores. Ores are usually contaminated with a large amount of impurities such as soil, sand, called gangue. Okay, and these ores are mixed with some other impurities like sand, clay, dust particles, soil, and etc. are present in that ore. That is the ore with these all impurities together we called as gangue, right? Gangues, how we can remove? Here we have the different separation techniques are there to remove the gangue. So some of the separation techniques I have given here. Gangues are removed by the various separation techniques based on the based on the differences between the physical or chemical properties of the gangue and ore. Okay, this is a gangue. So here one separation technique is a magnetic separation, here hydraulic washing. Okay, let us see further now. Now, extraction of metals from their ores involved mainly three steps. What are those? What are those? Concentration of the ore. That is we called as enrichment of ore. Just now we have discussed. Next one is the reduction to the metal, and the third one is the refining. Refining means the purification of the metal. We called as refining. Then how we can concentrate the ore? So the removal of the gangue from the ore by different methods are called as concentration of ores. What are the different methods are involved in the remove the gangue particles from the ore? Like magnetic separation, hydraulic washing, and washing with plenty of water. So that in that way we can separate the gangue from the ore, right? And steps involved in the extraction of metal from their ores. Here we have the mainly ore, we can classify it into three types: metals of high reactivity, metals of medium reactivity, metals of low reactivity. Okay, metals of high reactivity generally they are sodium, potassium, magnesium, salts of chloride and sulfates, right? And these salts we can separate it by doing electrolysis. Okay, electrolysis of molten ore. Now after doing this you will get the pure metal. Okay, the metals of high reactivity, how we can separate? By using which process we can separate? By taking this electrolysis of molten ore. By doing this electrolysis we can separate this pure metal. Now those metals which are having the medium reactivity, which are classified into again two types, those are carbonate ore and sulfide ore. This carbonate ore we can convert into metal oxide in the process of calcination. This sulfide ore we can separate it as metal of oxides of metal in the process of roasting. Calcination means you are just heating the ore to remove the carbon dioxide in absence of air. Okay, and this calcination and in the absence of air only we are heating the ore. So during that process what happened? The carbon dioxide removed as a gas, right? In the roasting what we are doing, this sulfide ore we are heating in the excess of oxygen. Then in that way we can remove the sulfide as sulfur dioxide. Okay, that process we called as roasting. After calcination and roasting, the metal converted into metal oxide form, then oxide of metal. When you remove the oxygen from the metal, that is we called as a reduction. When you do the reduction of metal oxide, you will get the metal. After refining, you will get the pure metal, right? And the metals which are having the low reactivity, so they are available in the sulfide form, and this sulfide ore what we have done here, the same thing we are doing here also, right? The sulfide ore what we are doing to separate the sulfur from that ore, we are just heating in the presence of oxygen, and that one we called as roasting. After roasting what happens? The metal converted into metal oxide form, and metal sulfide ore converted into metal oxide form. Further reduction, this we can get here metal. After refining you will get the pure metal. Okay, these are the steps involved in the extraction of metals from their ores. Now you see, in this slide we are discussing about extracting metals low in the activity series. Which are low in the activity series? Posokama, Gil, H, Chap, copper, silver, copper, mercury, silver, gold, platinum, and these are having the low reactivity in the series. For example, I have taken here copper and mercury. So mercury which is available in the cinnabar ore, like in the form of sulfide. The metals which are having low reactive in the series and available in their sulfide forms. Okay, mercury is available in the mercury sulfide, and this is also we called as a cinnabar. And the oxides of these metals can be reduced to the metals by heating. For example, you take the cinnabar. This is a ore of mercury. First, what you are doing here, we are just heating in the presence of air. This mercury sulfide on heating, what will happen? This mercury sulfide on heating in the presence of oxygen, it converted into metal oxide, that is mercuric oxide. Okay, the sulfide is evolved as sulfur dioxide gas. Okay, the sulfur ore converted into sulfur dioxide and it is removed as sulfur dioxide gas. Okay, so this metal oxide, when you heating further, then what will happen? This by simple heating we can get separate mercury from its oxygen, mercury from its metal oxide, right? So here we are getting mercury and oxygen. Is it clear? Right. So what we are doing the first step, we have taken cinnabar which is present in the HGS. Just in the presence of oxygen we are heating it. Then what will happen, this HGS converted into HGO, that is mercuric oxide, and also SO2 gas is liberated. Okay, the whatever the mercury oxide we get in the first step, and the next step what we are doing, just we are heating. And by decomposition of this is we called as thermal decomposition. We are doing by thermal decomposition means the one reactant split into two or more reactants. Okay, by doing this thermal decomposition we are getting here mercury which is in the liquid form. Right, now you see this is a mercury ore, and this is we called as cinnabar ore, which is the color of the cinnabar will look like this. Right, so after burning this in the presence of oxygen, so you will get this mercury oxide. Right, this is in the powder form. And heating further, this mercury oxide we get in the liquid form. This is the liquid mercury we will get like this. Okay, and this is the extraction of the mercury from its ore cinnabar. Now let us see now copper ore. Now you see this is a copper sulfur ore which is in the green in color. Right, what we are doing now, this copper sulfate we are just heating in the presence of oxygen. Now this copper sulfate converted into copper oxide, and it liberates the SO2 gas, and this is a red color powder we called as copper oxide. Okay, in the second step what we are doing, this we are doing the reduction, means you have to remove this oxygen from that metal oxide. Right, copper oxide. To remove this oxygen, what we are doing, we are taking some more copper sulfate. On heating, what will happen, and this copper oxide and copper sulfate in presence of heat, they will react each other and form the 6 moles of the copper and liberate the sulfur dioxide gas. So finally we will get the pure copper here. Okay, and in this way we can separate the copper from its copper sulfide ore. Okay, and move on to the next one, extracting metals in the middle of the activity series. Okay, then how do we extract the middle of the activity series, means we have your zinc, iron, lead, and these metals are having middle of the activity series. Means these metals present in the middle activity of the series, and these are present in the form of sulfides or carbonates. Okay, those metals which are those metals which are having a moderate reactivity and which are present in which form, sulfide ore and carbonate ore. Okay, then how do we convert it into metal oxide? That sulfide ore, in process of roasting, we can separate it into metal oxide, and the metal ore which are present in the carbonate form and metal carbonate form, by calcination process we remove that carbon dioxide, and finally we will get the metal oxide. Now let us see, these are the present in the sulfides or carbonates in the nature. It is easier to obtain a metal from its oxide, so the metal sulfates and carbonates are converted into metal oxides. And the first step involved here, the metal sulfides or metal carbonates, first you convert into metal oxide by process of roasting and calcination. Right, the sulfide sources are converting into oxide by heating strongly in the presence of excess air, and this is called roasting. What is roasting? This sulfide ore in presence of oxygen we are heating. Right, in presence of oxygen when you heat the ore, that process we called as the roasting. So in this process the sulfur is evolved as sulfur dioxide gas, and we'll get here zinc oxide, metal oxide will get in the solid form. Right, this process we called as roasting. And what is calcination? The carbonate ore just we are heating in absence of air. Okay, in absence of air, when you heat this, what will happen? This carbonate evolved as a carbon dioxide gas. Okay, finally we will get the here also metal oxide. Now this is a zinc sulfide ore, and this is a zinc carbonate ores. Right, the carbonate ores are changed into oxides by heating strongly in limited air, and this is called as calcination. Right, so in this both process, finally we are getting metal oxides. Now next step, you have to reduce this metal oxide. Then how do you remove this oxygen from the zinc oxide? By just reacting with the carbon. Carbon is a reducing agent. Okay, and carbon takes oxygen from the zinc oxide, and this zinc oxide converted into zinc, and this carbon converted into carbon monoxide. So this process we called as a reducing. Reducing means removal of oxygen from the metal oxide is called as a reduction. So in this process what we are doing here, just we are performing the reduction reaction, okay, by adding the charcoal powder or carbon powder to the zinc oxide. The zinc oxide converted into zinc, this carbon converted into carbon monoxide gas, right? Metal oxides are then reduced to metals by using reducing agents such as carbon, and also we called as a coke, okay, the pure form of coal we called as coke. An example, zinc oxide is heated with the carbon for the reducing to zinc. Here zinc oxide react with the carbon and it gives the zinc which is in the solid form. Reduction is also possible by displacement reaction. The highly reactive metals are used as reducing agent because they displace metals of low reactivity from their compounds. Example, okay, to remove the oxygen from the metal oxide, you can use the high reactive metal like sodium, potassium, aluminium. Okay, they can take the oxygen from the metal oxide. Because of their high reactivity, they can react easily with the oxygen and they can capture the oxygen from the metal oxide. Right, here one example is there. On heating manganese dioxide with the aluminum powder, you see, to remove this oxygen from the manganese, this manganese oxide we are heating with the aluminum, right? Then what will happen, this aluminum absorb this oxygen, and in this way this aluminum converted into aluminum oxide, and here we manganese, here we will get the manganese liquid, right? And during this process heat is evolved, and this is an exothermic reaction. Okay, so this is a manganese oxide powder. Okay, when you heat with the aluminum, finally we'll get like this manganese, right? Now extracting metals in the middle of the activity series. In this, these displacement reactions are highly exothermic. This is a continuation of this, and these displacement reactions are highly exothermic. So metals are produced in the molten state. Now you see, whatever obtained the manganese oxide which is in the solid form, after reacting with the aluminum, this manganese we are getting in liquid form, right? And these are the highly exothermic reaction. Because of that high excess heat, the metal converted into molten form, right, liquid form. And these reactions we are using in the thermit reaction. For example, you take the iron oxide, iron 3 oxide, and also we called as ferric oxide, and this is also we called as thermit reaction, and which are used to join the railway tracks, the broken railway tracks, which are used to join the broken railway tracks. Then how the reaction is going on, let us see now. When this iron oxide which is in the solid form, when it is react with the aluminium, so it will convert it into molten iron. This aluminium converted into aluminium oxide. During this process excess amount of heat is liberated. By using that heat, that iron, solid iron converted into liquid iron, and means molten iron you will get. The molten iron which are used to connect the broken railway tracks, and this reaction we called as thermit reaction, right? So in this thermit reaction, what happening here, the reaction of iron 3 oxide with aluminum is used to join railway tracks or cracked machine parts. This reaction is called as thermit reaction. In this reaction, ferric oxide which is in the solid form, okay, when you mix with the aluminum and when you heat this, you will get the iron in the molten form. Okay, this is the setup of the reaction. So in this setup we mix the iron ferric oxide with aluminum, and just simple heating, this what will happen afterwards, somewhat this iron converted into molten form. Okay, by using that molten iron we can join the railway tracks like this. Okay, is it clear everyone? Okay, now move on to the next one. Extracting metals towards the top of the activity series. Highly reactive metals cannot be obtained from their compounds by heating with the carbon. Carbon cannot reduce the oxides of sodium, magnesium, calcium, aluminum, etc. because they have more affinity for oxygen than carbon. Okay. And these metals are high reactive in nature, sodium, potassium, and whatever this calcium, sodium, magnesium, calcium, and they are very affinity towards oxygen. They won't leave its oxygen from its okay, and they don't want to leave the oxygen from their compound. And when you adding the carbon, they won't give its oxygen to the carbon. Why? Because these elements or these metals are more affinity more affection towards the oxygen, right? So in these cases, so what you have to do here, you have to approach the electrolytic reduction. So in this process, what you are doing here, these metals are obtained by electrolytic reduction. So in this process, what happens, let us see now. Sodium, magnesium and calcium are obtained by electrolysis of their molten chlorides. Okay, the metals are deposited at cathode, that is negatively charged electrode, and chlorine is liberated at the anode, right? So here what is happening here, we are taking some molten NaCl, we are not adding the water, just the liquid form of NaCl we are taking, molten NaCl we are taking. Okay, in molten NaCl consists two ions, Na plus ion and Cl minus ion. The Na plus, before that you are taking molten NaCl, just you are keeping the two electrodes. One electrode you have to connect it to the positive terminal of the battery, and other electrode you have to connect it to the negative terminal of the battery, right? The electrode which is connected to the negative terminal of the battery, which is called as cathode, which attracts the cations. Okay, the electrode which is connected to the positive terminal of the battery is called as anode. At anode, liberation of chlorine gas takes place, right? And this Na plus attracted towards by negative electrode, and this Na plus deposited as Na, sodium, and the sodium plus ions and sodium ions deposited as sodium on the cathode electrode, right? And this Cl minus ion attack towards this positive electrodes, where the discharge of Cl minus takes place. The Cl minus discharged as chlorine gas here. Means here we can observe some air bubbles due to evolution of the chlorine gas. So in this process we get the sodium. Okay, all sodium atoms get deposited on this cathode. Now at cathode, what happened, this sodium ion takes electron from the cathode, right? Why? Because here negative charge electrodes gives the electrons, all positive sodium ions take that electron, and the sodium after taking sodium ion after taking electron, it converted into sodium atom, okay, sodium metal atom, which get deposited on this cathode electrode. And chlorine minus, after removal of two electrons, it liberated as chlorine gas. Okay, at cathode gaining of electrons takes place, and also we called as reduction. At anode, loss of electrons takes place, which is called as oxidation. Okay, similarly aluminum also can obtained by this method, electrolytic reduction method, by using the aluminum oxide salt, aluminum oxide, right? Now here we have one more process is there, electrolytic refining process. So in this process, this is the last step, electrolytic refining. To get the pure metal, we are doing this process. So in this method, how we are separating this impure copper from the pure copper. Okay, how we are separating impure copper, how we are separating copper from the impure copper, right? Now let us see now. The metals produced by the reductions are not very pure. Okay, by reduction process we are not getting the pure metal. Okay, to further purification, so we are applying this electrolytic refining process. In this process, what we are taking here, it is the most widely used method for the refining impure metals, right? Metals such as copper, zinc, tin, nickel, silver, gold, etc. are refined electrolytically. And in this process, impure metal is made the anode, and the thin strip of pure metal is made the cathode. A solution of metal salt is used as an electrolyte. Now you see, in this process we are taking the copper sulfate solution, okay, CuSO4 solution. Okay, this is we are used as electrolytic solution. So in this we kept two electrodes. One is having the impure copper, and other one is having thin strip with the pure copper. And this thin strip with the pure copper we connected with the negative terminal of the battery, right? And the impure copper strip electrode we connected to the positive terminal of the battery. Okay, when you switch on the battery, then what happens here, the Cu plus which are coming from here, the Cu, just it comes in the solution as Cu plus, and this attracted towards this negative electrode, and it will deposited as Cu. Means this is the impure one, right? So from this, just we are taking copper only, right? How that copper is coming from this impurity? Yes, impure electrode, because of these charges. Okay, here we connected with the plus charge, then copper comes to the solution as a copper positive ion, and this copper positive ion next deposited as copper on the negative electrode. Okay, Cu plus attracted towards the negative electrode, right? So in this way, this pure copper get deposited on this thin strip. Okay, so in this way we are refining the metal. The impurities whatever there in this electrode, which are collected at the bottom of the vessel, right? Here we can see these impurities. So in this process we are purified the metal. Okay, now next topic is corrosion, right? Any article you can see, so these are the iron nails. After getting rusting, so after reacting with the moisture air, it will convert it into like this ferric oxide form. Now these are the some pipes are there. After getting corrosion, so the color of this metal get changed. These are the silver spoons. After getting corrosion, so the color of this metal get changes. Okay, then how to avoid this corrosion? What are the how to prevent this corrosion? Let us see now. And before that, what is corrosion? Silver articles become black after some time when exposed to air. Now you see here silver spoons are there. When you exposed for some time air, then what will happen? The silver color is changed to the black color. This is because it reacts with the sulfur in the air to form the coating of silver sulfide. Okay, in atmospheric air there are some sulfur molecules. Let us assume there are sulfur molecules. This sulfur gas reacts with the silver spoons, and the silver sulfide is formed, which is in the black color. Next you see the copper here. When copper reacts with the atmospheric carbon dioxide, it will form the copper carbonate, which is in the green in color. CuCO3 will form, right? So this slowly loses its shiny brown surface and gains a green coat, and this green substance we called as basic copper carbonate. Okay, iron when exposed to the moisture air for a long time acquires a coating of a brown flaky substance, which is called as rust. When you these iron nails, when you expose to the air, in the air the moisture and air is present, because of that this iron converted into Fe2O3, that is we called as ferric oxide, and also we called as rust, right? Now how do you prevent this corrosion? Prevention of rusting of iron: painting, oiling, greasing, galvanizing, chrome plating, anodizing or alloying. These are the methods to prevent the corrosion. Okay, by greasing, by painting, but oiling, or chrome plating, or galvanizing the steel with zinc, or anodizing articles. By using this method we can prevent the corrosions, right? What is galvanization? Galvanization means, in the reactivity order, Gil is there, zinc, iron, lead, right? Zinc is more reactive than iron. When iron articles are coated with the zinc, then iron gets prevent from the corrosion. Means the low reactivity metal, on low reactivity metal, when you apply the high reactive metal as a paste, that process we called as galvanization. Galvanization means coating of steel and iron with a thin layer of zinc to protect from the rusting, we called as galvanization. Okay, to protect the iron articles, just we are coated the zinc. Means zinc is having high reactivity than iron, then zinc will get first corrode. So in this process we protect the iron. The galvanized article is protected even if the zinc coating is broken, because zinc is more reactive than iron and hence can be easily oxidized, right? We are coated with high reactive metal on low reactivity metal. So iron is having low reactivity compared to the zinc. So here what we are doing, just it is the coating of steel and iron articles with the thin layer of the zinc. So in this way we are protecting the rusting. Then zinc can react, then iron prevent from that rust, right? So in this way we can protect the iron articles, right? Next one, examples here we have. Pure iron is never used to prevent the corrosion. So just we are adding some 0.05% of the carbon to become hard and strong, and it is non-corrosive also. Stainless steel, and which is we called as stainless steel. Stainless steel do not get corrode. Mixing iron with mixing iron with nickel and chromium forms stainless steel. It is hard and does not get rust. Okay, these are the stainless steel. To make this stainless steel, what we are doing here, we are mixing this iron with nickel and chromium, and it will form the stainless steel. Okay, and it is hard and does not get corrode and does not rust also. and pure gold. And 24 carats gold is very soft, so it is not suitable to make jewelries. To make it hard, then what we are doing, it is allied with the silver or copper to make it hard. So in India, 22 carat gold is used to make ornaments. 22 parts pure gold means 2 parts copper or silver. Okay, 24 carat gold, in the 24 carat gold we are using the only 22 carats 22 parts of pure gold. To this we are adding the 2 parts of copper or silver to become more hard. We are doing like this. Okay, now here some other applications are there. The alloy containing mercury is called an amalgam. Okay, and this is we called as tooth amalgam, when mercury is mixed with other metal and it will form the amalgam. Electrical conductivity and melting point of an alloy is less than that of pure metals. Example, when you make like this, brass is a combination of the two metals, that is copper and zinc. Bronze is a combination of two metals, that is copper and tin. These are the not good conductor of electricity, right? Solder, it is alloy of lead and tin. This is a solder, this is alloy of lead and tin, has a low melting point. It is used for the welding electrical wires. Okay, it is used for the welding electrical wires. These are some applications to to prevent the corrosion and to make it more hard. What we are doing here, we are preparing alloy. Alloy is the mixing of two or more metals. Okay, the wonder of ancient Indian metallurgy. Now you see the iron pillar built 1600 years ago near the Qutub Minar in Delhi. Has high quality of rust resistance. It is 8 meter high and weighs 6 tons. Okay, after 1600 years also it won't get rust now, right? And this is about metals and non-metals, right? So if you like this video, please subscribe, share, like and comment. Thank you for watching. Have a nice day. Bye.